The name of this video is Maxwell inductance. Taylor. This is in fact the last video about Maxwell inductance, where eventually we're going to find the final result for the self-inductance of a loop, a quasi-filiform loop, carrying a current by means of Neumann integrals. So we go from the mutual inductance to the self-inductance. Again, a solution given by originally Maxwell. So let me first remind you that in the limit for which for A, capital A that goes to small a, that is, we are making the radii of the two loops, which gave us the mutual inductance, to be the same, and the two loops, they're still at a distance small delta from each other, which again is going to emulate the radius, capital R, the cross-section of the wire, of the quasi-filiform wire. Under these conditions, let me rewrite down our previous result, which now M to 1, the mutual inductance, effectively in this limit becomes approximately the self-inductance, which approximately, the reason why for this double approximately, this is because we are still just emulating the mutual from the mathematically from the self from the mutual, and then the expression we found in the previous video was using the Legendre series for the elliptic integral, so it was also approximated to make a back of the envelope calculation. So if I look back at the result from before, assuming that now capital A is small a, this is equal to minus mu naught. There was a square root of capital A, which is just small a now, since they are the same. And in the bracket, I just remind you our previous result, which I had written down here, is going to be 2 over k minus 1/4 k1 square. These were the two terms without the natural logarithm, plus the natural logarithm of 4 over k1, and let me open a parenthesis, let me put what is the 4 terms associated with the natural logarithm here is k plus 1/4 k1 quantity square minus 2 over k minus k1 square over 2k from the previous video. 4 terms, 1, 2, 3, 4, with the natural logarithm. Great. This was using the Legendre series, which approximate the elliptic integrals of first and second kind f and e. All right. So now, with that in mind, let us look a little bit more closely at the modulus of the elliptic integrals, which is k. In fact, let's compute k square. So eventually here we need k, k1 square, and k1. So let's start from k square. It's simpler to do that. So again, the aim is we need k, k1 square, and k1. But let's start, as you will see, this is useful, from k square in this limit. K square, which is the square of the modulus of the elliptic integrals, is 2 times root of AA, and so it becomes, squaring it, 4 times small a quantity square divided by 4 times, because it was the root of a plus a square, not under square root because I'm squaring it, plus delta quantity square. This, by dividing numerator and denominator by 4a square, can be rewritten suitably as 1 divided by 1 plus delta divided by 2a, the whole quantity square. Now this quantity here, delta over 2a quantity square, including the square, we call it xi. So the xi is small because delta is small. So xi is a small quantity because we want the distance between the two loops to be small. In principle, we want it to be 0. The reason why we don't want to be exactly 0 for delta is because we want to emulate the fact that the wire has a cross-sectional area. Okay, if it was filiform, you could go basically delta equals 0, but we don't want that. We want to make it a little bit more realistic. Okay, this is actually the contribution due to Maxwell. All right, so then we do that, and now, since the xi is small, this is a small quantity, we can perform Taylor series and stop it to the first order. In fact, to be precise, it's a Maclaurin series, what we're about to do. And so now, in this next step, we are using another series, which is a Taylor or Maclaurin series. So you see, that's the way physics works. This is the way science works. You need to make the right approximations. It's the art of approximations, like Enrico Fermi used to say. Physics is the art of approximations. And here we are doing all the right approximations. Of course, if you do the wrong one, you get completely bizarre results. So you need to really think about the physics, which is this limiting, going from M to L, and then try to adjust your math around the physics, which is the final aim. The math is just the tool to get to the final aim, okay? All right. So now, since this is small, we can perform a Taylor series, and so this can be rewritten effectively as 1 divided by 1 plus psi, which by tailoring it is simply 1 minus psi. All right. Because in the denominator, if you just tailor it, is 1 minus psi. Great. So now we have this first piece of information here at hand. The next thing we need, actually, we don't need k squared, we need k1 squared. So k1 squared, from the definition of the modulus of the Legendre series for the elliptic integrals, is 1 minus k squared. So if I just do 1 minus k squared in the limit, in the Taylor series limit, it's 1 minus 1 is plus psi, which also means, so we have the first thing we wanted to have, it was k1, now we have it. K1 we need it, here, here, and here. Oh, this is square. Okay, so k1 we have it. K1 squared. So k1 squared we have it, k1 squared we have it, k1 squared we have it. Now we need k1, okay? We need it in the argument of the logarithm. That's the only place where actually we need it. So k1 is nothing but the square root of k1 squared. So it's the square root of psi. And we are going to need it here. Finally, we also need k, but k is very simple because k is the square root, of course, of k squared. So it's the 1 over square root of 1 plus psi. And if you tailor this one, you should know the result is 1 minus 1/2 psi. Great. Now, one thing you need to notice here is that in all this series, as it turns out, the key thing here to note is that psi goes to 0 plus s, let's see, our definition of psi is delta squared, which is a small quantity, whereas the square root of psi goes to 0 plus s just delta. Between these two, which one is the higher order term which will not contribute to anything? Clearly, this one. So we will only focus on these terms here, square root of psi. Let's see how that works. So what we do now, we plug in all these Taylor series, or Maclaurin if you want to be more precise, okay, because they're on the origin, inside this equation, therefore obtaining a new equation, which is going to be m, in this case m is already L, let me call it just L, we already are in the limit, so this is our self-inductance. So the self-inductance L is going to be approximately given by minus mu naught A, and then what do we have? Okay, let's plug in all these series. 2 over k, where is our k? So let me highlight all the various things we need here. So k1 is psi, k1 squared, k1 is square root of psi, and k is 1 minus 1/2 psi, okay? So 2 over k is going to be here, 2 divided by k, which is 1 minus psi half. Then we have minus 1/4 k. But what is k? K is again 1 minus psi half. And what is k1 squared? K1 squared is just psi plus the natural logarithm of what? 4 divided by k1. By k1 is nothing but square root of psi. And then what do we have? In parentheses here, we have k, and k is 1 minus psi half. we have plus 1/4 k1 square. So plus 1/4 k, but k is 1 plus psi half. K1 square is just xi. So we are at the second term, minus 2 over k, minus 2 over k, and 2 over k is like the first one, so it's 2 over 1 minus psi half, minus k1 square over 2k, which is k1 square is psi, divided by 2k, which is 2 times 1 minus psi half. In fact, let's open here a brace to be more precise. Like this, okay? Let's not forget that there is a small a there. All right, now let's perform a few approximations, okay? So we know that only square root of psi is what matters. So anything with psi, we can neglect it. So this one in the denominator doesn't matter. So here the result of this ratio is just 2. This whole quantity is multiplied by psi, so this whole quantity goes away. Here, 1 minus psi half, the psi half goes away. This whole quantity is multiplied by psi goes away. Psi half goes away, so this is just minus 2, and the psi divided by whatever goes away. So at the end of the day, after all these approximations, we can rewrite our L as minus approximately mu naught A. Now we should have only 2 terms left, so we have, in fact, just 2 divided by 1, which is 2. Then so all these quantities go away. The logarithm multiplies 1, nothing, 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 minus 2, which is minus 1. So it's minus the natural logarithm of 4 divided by square root of psi. This is what we are left neglecting higher order terms. So this can be rewritten as minus mu naught A, 3 terms, 2 properties of logarithms, minus the natural logarithm of 4, plus, because it's minus, but in the denominator it gets a plus, natural logarithm of square root of psi. But what is square root of psi? So let me remind ourselves what is the square root of psi. Square root of psi, from our definition here, actually from this definition here, square root of, if psi is delta over 2a squared, square root of psi is just, so this quantity is just delta over 2a. So we can further use the properties of logarithms and eventually find something with 5 terms now, L approximately equal minus mu naught A times 2 minus natural logarithm of 4. Here we have the natural logarithm of delta in the numerator, so plus natural logarithm of delta, which happens to be in the numerator, divided by, so minus the natural logarithm of 2, minus the natural logarithm of small a. And this is 1, 2, 3, 4, 5 terms. Let me cross-check that they're all correct. 2 minus logarithm of 4, plus 1 delta, minus logarithm of 2, minus logarithm of 8. Perfect. These are exactly the terms we want. Okay. So far, so good. So now, what we want to do next? Now, physics come back. So this was all math. Now the math is finished. Okay? Now we go back to physics. And now it's Maxwell that comes into the game here. So what Maxwell tells us is that we need to consider the fact that we have a cross-sectional area associated with this quasi-filiform wire. So the cross-sectional area is pi r squared, that is a circle with radius capital R. Now let me ask you this question. What is, on average, if I pick 2 points, P1 and P2, capital P1 and capital P2, inside this circle, what do you think is an answer for the average distance between such 2 points? Okay, so if I want the distance between those 2 points on average, what kind of average I'm going to get? Well, let's call this average small delta. To first order, I would say a good approximation would be capital R, because you see at most 2 points on average will be the distance will be approximately the radius between them, right? They are contained with this within this quantity, so let's say a capital R. So if now you emulate with delta equal to capital R, this delta in this equation here, you get a result which is a reasonable approximation for the inductance of this wire, okay? So this delta, as we said, emulates the fact that there is a cross-sectional area here. But, and remember that I'm considering basically two axes which are within this cross-sectional area, and so they are always at a distance, which is the one we go in the limit to 0. This delta, remember the first video about this. So we need to emulate this fact. And as it turns out, there is a better way to emulate it, which is a harmonic mean. The harmonic mean, instead of being R, tells us that delta is going to be a prefactor e to the power of minus 1/4 times capital R. This is called harmonic mean. So if you use the harmonic mean, and this is what Maxwell came up with, then the result is even a better approximation. So now let's use this harmonic mean, which emulates the fact that there is a cross-sectional area with our result, to finally find the final result here. So in the last step now we go to physics, so I change color, and so here L is going to be approximately equal minus mu naught times the radius A of the circle. You can call it capital A, it's the same thing. Now we have delta. What is delta? Delta is e to the minus of 1/4 times R. So the logarithm of e is just the exponent. So we get 2 times. These two, we can already multiply them. So it's minus logarithm of 8, 4 times 2. So this is taken into account, this is taken into this account. This one gives us minus 1/4 and plus the natural logarithm of capital R. So this one is taken into account, minus the natural logarithm of A. Okay, so now we have 2 minus 1/4, which is 1.75. So L is approximately given by minus mu naught. A, quantity 2 minus 1/4, which is 1.75. 1/4 is 0.25. And then we have minus log natural logarithm of 8, RA. So this has to be nothing but R divided by 8A. So it's plus the natural logarithm of R in the numerator, positive, divided by 8 times small a. And guess what? This is the final result, mu naught A, 1.75 plus the natural logarithm of 8 over RA. If you Google for the inductance of a loop inductance, this is what all the calculators will give you, the loop inductance given here, which incidentally is one of the most important inductances you can get out there, because we use loops all the time. So a coil, it's a single loop, right? It's a very important result that we need a lot in physics. Not only is important, but this methodology, there is a book from NIST where they use something like this. They don't explain all the math, they just give the results because somebody did it at some point in time, with thousands of pages, I think 600 pages, where they find, by means of a similar approach, the inductance in a back-of-the-envelope calculation like this, so giving a finite result, not numerically, of all possible structures, like a rectangle. So you can try to do the inductance of a rectangle, right, or a square, so a loop which has a shape of a square, or any other shape you want, and it's all based on this kind of concept. So if you grasp this, you learned a lot about science, how to find the right references, to think about the physics, which then, and to match the right math to that physics, and then you go into the math, and then finally, you go back into the physics to find the final result. So physics is a combination of math and intuition, and you need to put it together. So the math is also important because you need to give solutions eventually. Of course, you can do this numerically, but I really think as a scientist, you really want to learn this scientific method, this technique, which we use as researchers all the time. I think this is a beautiful result. I hope you appreciated it. Thank you. That's it.